All right, welcome to the Chapter 8 lecture, and we're talking today all about chemical bonding. So how are things put together, and why do they make the kinds of things that they do? And we're getting much deeper into things that you kind of already know a little bit about, and we're going to talk about all kinds of new things. So starting with Chapter 8, the textbook starts talking about ionic bonding. Right, and so that's a bonding of a metal with a non-metal, which we already kind of know about. And the important thing about ionic bonding is that the thing that distinguishes it from other kinds of bondings is that it is a transfer of electrons. Okay? As opposed to a sharing or any other kinds of thing, ionic bonding is electrons actually trading places so that things can come together via electrical charge. So a very simple example, and most often when we talk about ionic bonding, simple examples are best to start with. Things like sodium with chlorine. Okay? And what I'm drawing here are Lewis dot structures. Lewis dot structures. Okay, and Lewis dot structures simply are you list the chemical symbol, and you give a dot. You show a dot for every valence electron that particular element has, and we talked about determining valence electrons before, where if you're on the non-metal side of the table, you start at the noble gas and you count backwards from 8, and then you skip the transition metals and you continue on. So if you count backwards from 8 all the way across, you get to sodium, and sodium has 1 valence electron, hence a single dot. Okay, chlorine has 7 dots, 7 valence electrons. Okay, so when sodium and chlorine get together, and we've kind of already talked about the desire for elements to become like a noble gas, to have the same electron configuration as a noble gas. What happens is that if sodium loses 1 electron, it becomes just like a noble gas, or the same electron configuration as a noble gas. And if chlorine gains an electron, it also becomes has the same electron configuration as a noble gas. So what happens here is that the electron actually gets transferred over, and the result is that we have a sodium ion with no valence electrons and a chlorine ion with 8 valence electrons. Okay? And the important thing about that is that now, both of these have noble gas configuration. Okay? And the sort of defining characteristic of a noble gas configuration is 8 valence electrons. And that's a weird symbol. I'm going to get rid of that real quick. 8 valence electrons is the important thing. This is referred to as the octet rule. Okay? 8 is a very stable place to be. To have a full S shell and a full P shell, to have 8 valence is a particularly stable place to be. Okay? So when I'm showing these ionic scenarios, the positive of the sodium is attracted to the negative of the chlorine, and that's how they are held together, is through electrostatic charge. Electrostatic attractions. Okay, so this is why ions or ionic compounds form, is they transfer electrons, and then that positive and the negative stick those two ions together, and then you start to form crystals and all kinds of wonderful things. So when we're talking about forming this stuff, there is a particular way that things go together. And this attraction is called lattice energy. Right? The energy associated with ionic attraction is called lattice energy. Okay? And lattice energy is, it takes a lot of, in order to determine lattice energy, there's a lot of steps. And what I'm going to go through right now is something that's a bit extreme. You won't actually have to calculate this, but I'm going to show it to illustrate a point. Okay? So to calculate lattice energy, there is a process called the Born-Haber cycle. Okay, and the point is that the Born-Haber cycle tells us the energy given off when separate ions come together, separate gaseous ions come together, and that's the lattice energy. And if you're trying to follow along with the posted handwritten notes, this is at the very, very end. So I'm going a little bit out of order with my handwritten notes. But I think that this order is actually more productive for this format of lecture sort of thing. So energy given off when separate gas ions form 1 mole of solid ionic compound. Okay, so the way this works is that there are steps. Okay, so I'm gonna write down the steps, and then we'll go through the steps. So step 1 is sublimation. Okay, we want to make everything a gas. Okay, step 2 is atomization. We need to make everything a single atom. Okay. Step 3 is ionization. And as you might expect, we're going to make everything ions. Okay. Step 4 is formation. We're going to make a solid. And 5, we're going to solve for the missing energy. Okay, so there are 5 steps to doing the Born-Haber cycle. And we're going to see if I can actually make this fit on my screen in a reasonable fashion. Okay, so what we're going to do is we're going to, and here's an important thing, is that all of this information, the sublimation, the atomization, the ionization, the formation, all this stuff is found in tables. Okay, these are all tabulated values of delta H. Okay. Okay, so these are all enthalpy values, and we're going to use Hess's law, and we're going to basically add up the steps. So let's look at the formation. Let's see if we can figure out what is the lattice energy for sodium chloride. Okay, because that's a very common one for us to use. And I'm going to start here. So first of all, I've got way down here, okay, and this is all based on energy going this way. Okay, so energy increasing going up the thing that I'm about to draw. So the first step is I know what the delta HF of formation for sodium chloride solid is. NaCl solid. Okay, I know what that value is, and it's equal to negative 411 kilojoules. Okay, so right away I've got that distance. I know how much energy that is. Okay, so my next step, so that's where I'm beginning from. I know what that delta HF is. So step one is sublimation. So I'm gonna go from solid sodium and chlorine gas, okay, and I'm gonna sublimate the sodium. Okay, sublimate the sodium, and I have a delta H1, I'm going to call it delta H1, is plus 107 kilojoules. Okay, so that's my step one. So now I'm at sodium gas and chlorine gas. Great, cool. All right, so now step two is to atomize. I need everything single atoms. So right now I've got this 1/2 chlorine gas here, but technically it's still Cl2, okay? But I want it to just be Cl. So I'm going to atomize my chlorine gas. We're gonna come up here. Atomize the chlorine, and that has a delta H, we're going to call this delta H2, equal to plus 122 kilojoules. All right. So now I have sodium gas and just a single atom of chlorine gas. Okay. So now I need to make ions. Okay, so the first thing that I'm going to do is I'm going to ionize my sodium. And that is going to make my sodium now sodium plus, and that has a delta H, call this delta H3, 496 kilojoules, right? Because it always takes energy to pull off an electron, right? So now, and these are all the steps. Sodium plus gas, so I have a sodium ion in the gaseous form, and chlorine, neutral chlorine, right here, okay? So at this stage, I have one ion and one neutral atom, but I need two ions to come together, right? So I'm going to extend my line over here, because now I'm going to drop down in energy, because it actually is beneficial to chlorine to become an ion, a negatively charged ion. So we're going to drop down some energy here, and we're going to make this Na plus gas and Cl minus gas, and that has a delta H, call this delta H4, equal to negative 349. Okay, so now I've got two ions, two atoms, right? So I've accomplished everything. I've finished step 3. So now my last step is to form my solid, okay? And that is going to be all the way down here to make my solid. Okay, and that's delta H5, and that is equal to, that is the lattice energy. Okay, so let's see if I can sort of label this business. So here's step 1, here's step 2, here's step 3, also step 3, here's step 4, and my final step, step 5, is to solve for the missing energy, and that's the lattice, okay? So let's sort of walk through that action a little bit. So hopefully you've been keeping track of all this good business here, and because I need a little bit more room. So delta H of formation is equal to delta H1, delta H2, delta H3, delta H4, and delta H5. Whoops. Okay, so delta H1 was our sublimation. Delta H2 is the atomization. Delta H3 is the ionization. Delta H4 is the other ionization, and delta H5 is the lattice energy. Okay, so we're going to plug everything in and solve for the lattice energy, and we find out that the delta H5, I'm not going to belabor writing in the numbers because I don't expect you to calculate this. This is mostly a demonstration. The lattice energy comes out to be 787 kilojoules, right? And I do challenge you to try to figure this out on your own as far as the math goes and all that good stuff, but you don't have to. So really the whole point of going through this process is to illustrate a point. So most importantly with the ionization steps, okay? So this step and this step, all right, these ionization steps. So imagine, so in this spot right here with the ionization of the sodium, I'm only pulling off one electron. If I had to pull off another electron, say if I were talking about something like magnesium, which makes a 2+, if I have to pull off another electron, that costs more energy still. And that would cause the ionization energy to increase even more. And then if I were combining it with something that makes a 2- ion or a 3- ion, that changes this energy over here. Okay? So the point of showing this whole Born-Haber process is to illustrate the effect of charge on the lattice energy. Okay? So in terms of what you'll need to be doing with mastering chemistry, there is a question or two where you have to evaluate lattice energy just based on the species or the compound that's being made. And the easiest way to look at that is with an equation that's in the textbook. So the energy of the electrostatic attraction is related to a constant K, Q1, Q2 over D. Okay, so D is the distance between the ions. And it's related to ionic radii. Okay, so if you can imagine, if you've got a couple of really big ions, really large ions, that energy is going to be smaller. all right? Because if I have large ions, I have big ionic radii, that increases the value of the denominator, which makes the energy smaller. Q1 and Q2, these are the charges of the two different ions. Okay, so this Q1 could be a +1, Q2 could be a +1, could be a +2 and a +1, could be, or excuse me, not pluses, what am I saying? These should be minuses, right? But we're really just looking at the numerical value regardless of sign, okay? So looking at this equation, we want to pay attention to the fact that as the charges get larger for the individual ions, that pushes up the energy, the lattice energy. As the ionic radii get larger, that pushes down the energy. Okay, so just based on periodic trends, which we talked about in the last chapter, we can just look at what we know in terms of radii, and we already know about charges. So the important thing here is that bigger charge, and this is one that you want to pay attention to, bigger charge gives us bigger lattice. Okay. Smaller radii gives us bigger lattice. Okay. So looking at periodic trends, let's look at a couple of examples of different compounds, ionic compounds, and take a look at how their lattice energy compares based on what we know from periodic trends, okay? So if I'm talking about the lattice energy in kilojoules per mole, I have some examples. So if we have lithium fluoride, right? Lithium is one of the first things on the table. Fluoride is in the upper left. We have a lattice energy of 1,030 kilojoules per mole. Lithium chloride, just one step down from fluorine in the periodic table, has 834. Okay, so let me put this energy of the lattice equals K Q1 Q2 over D. All right, so paying attention to the those guys. Lithium is the same in both compounds, right? So, and in both cases, I have a +1 and a -1, and a +1 and a -1. So the charges are the same, okay? So the numerator of my energy equation isn't changing, right? Q1 and Q2 are 1 and 1, nothing's different, right? And that K constant doesn't change. What is changing is the distance between them. Which is larger, chlorine or fluorine? And hopefully you immediately said chlorine is bigger because fluorine is one of the smallest atoms or elements on the periodic table. So if D is getting bigger in that equation, that means that the energy should be getting smaller. Okay? If I continue on this path and I look at lithium iodide, 730 kilojoules per mole. Okay, iodine is bigger than chlorine. So again, my D is getting bigger, my energy is getting smaller. Okay, so let's shift the focus a little bit and let's look at something like magnesium chloride. Okay, now I'm dealing with a +2 and a -1, right? So now I'm starting to play with charges. Okay, so watch the dramatic increase. Huge, right? More than twice what lithium fluoride would be, just by changing one charge in that equation. Okay, So all I've done is really, magnesium's actually a little smaller than lithium. Chlorine's a little bit bigger than fluorine, but wow, what a difference, okay, by changing charges. Let's do it again. Right, so now I've got a +2 and a -2. Now we bump it up even harder, okay? Let's go even further. Let's go with scandium nitride. Not scandium, tin nitride. My bad. Right? So tin is a +4. Nitrogen's a -3. And look where we get. Okay? So distance makes a deal, so ionic radii, and charge makes a deal, right? And you can get a qualitative sense just based on periodic trends, okay? Things that you already know as far as charge and ionic radius. Okay, so the next thing that I want to talk about is the topic of polarity. Okay, so polarity, and the term we often use is a thing called dipole moment. Okay, and I'll explain what that means here in just a second. But I'm going to switch really quick to a different image. Okay, so what we have here, these are what are referred to as the Pauling electronegativity values. Okay, and this comes from a very, very talented and famous scientist, Linus Pauling, and he experimentally determined the electronegativities of pretty much all of the elements on the periodic table. And what we find is that fluorine is the most electronegative element on the periodic table. Okay, and remember that electronegativity is the ability to pull electrons in. Okay, so depending on where you are in the periodic table, you have a greater or lesser ability to pull electrons toward you, okay, to anthropomorphize this thing a little bit. But what we see is that our metals, especially these guys over here on the left-hand side of the table, have very, very low electronegativity values, okay? And as we go down the table from lithium to cesium, they get even smaller, right? And then as we go to the right and up towards fluorine, the electronegativity values increase rather dramatically. Okay, so the point with electronegativity, wrong button, is that if I have, for example, a bond between hydrogen and fluorine, okay, what's really happening here is that, yes, this is a not an ionic bond, so the electrons are shared rather than transferred, but the electrons spend more of their time around the fluorine. Okay, so if this red, ugly thing that I've just drawn is sort of a depiction of where the electrons live most of the time in this molecule, they spend most of their time around the fluorine. Okay, and the most common way for us to draw that, to indicate that, is with an arrow. Okay, and the arrow shows us the direction that the electrons go. We say the direction of negative charge. Okay, so the arrow points in the direction of the negative charge, which means that the fluorine side of things, and we use a little symbol, Greek delta, a little squiggle, the fluorine side has a negative charge to it, and the hydrogen side has a positive side to it. Okay, and when I was in Gen Chem and learning all this stuff, I had a hard time figuring out which end of the arrow was telling me what, until I clued on to the fact that this is why we have the cross. That little crosshatch is a positive symbol. Okay, so if you're ever in doubt, whichever side is positive, put the crosshatch there and then point the arrow the other direction. Okay? But the moral of the story here is that because fluorine is more electronegative than hydrogen, the electrons spend most of their time around the fluorine, all right, making that side of the molecule negatively charged. Now, let's come back to this idea of the electronegativity values, those numbers, right? So my electronegativity value for hydrogen is a 2.1. My value for fluorine is a 4.0. The difference in those two values tells whether it's polar or not. Okay? And to come back to this idea or the term, the dipole moment, right? So in science and other places, when we want to talk about two things, the prefix for two is di, and we're talking about a positive pole and a negative pole. So if something has two poles, we say that it has a dipole moment. Okay? So the difference here with hydrogen and fluorine is a 1.9. Okay? In favor of the fluorine. Okay? The idea here is that fluorine has a bigger value. All right? It's a 4 versus a 2.1. So fluorine is more electronegative. That means that the electronegativity difference is it's in favor of the fluorine, which means that the electrons go where the fluorine is. Okay? So with that, we have some guidelines for determining types of bonds that we get depending on electronegativity. Or from polarity. Okay? So if the electronegativity difference is from 0 to 0.4, we say that that is a non-polar bond. Okay? So basically, if it's small enough, that difference is insignificant, and it actually does not play much of a part in anything. So we just basically write it off and say it's a non-polar bond. If the electronegativity difference is between 0.5 and 2, then we say that it is a polar bond. Or it has a dipole moment. Okay. If the electronegativity difference is greater than 2.0, guess what? We say that it's ionic. Okay. So let's look at an example. So how about the electronegativity difference in sodium fluoride? All right. So sodium has an electronegativity value of 0.9. Fluorine is a 4.0, right? So we have a difference of 3.1. Totally ionic. Right? And you'll find that when you look at the electronegativity values, that's going to be the case across the board. Anytime you bond a nonmetal with a metal, or almost any time, you are very, very likely going to get an electronegativity difference of greater than 2, which makes it an ionic bond. Okay? Right. So we've spent a lot of time talking about polarity and about ionic bonds, so let's talk about covalent bonds now, okay? So that's a big part of this chapter, is covalent bonding. Okay, so unlike ionic bonding, covalent bonding is a sharing of electrons. Not transferring, but sharing. Okay, that's very important. So rather than transferring, we're going to look at a situation like this. So CO2, right? 2 nonmetals making a compound. If I draw Lewis dot structures for these atoms, it's going to look something like this, right? So each oxygen has 6 valence electrons and carbon has 4. And what's going to happen is that everybody still wants to get to 8, right? The octet rule still applies here, but we're not going to make ions. We're going to share electrons, sort of in a socialist, communist sort of mindset of, if everybody has access to the electrons, let's all get there, okay? So the idea here is that I'm going to share those 2, and I'm going to share those 2, and I'm going to share these 2, and I'm going to share these 2, okay? And the result is something that looks a little bit like this. Carbon, oxygen, oxygen. Okay, same number of electrons, but now I've just sort of drawn this a little bit differently. And the result is that each atom has access to 8 electrons. Right? That's the important thing, because that gives us a noble gas configuration. Right? So let's sort of zoom in a little bit and sort of take a look at what's going on here. So the oxygen feels like it has access to all those electrons, right? Which means that there are 8. It has the ability to access 8 electrons. Let's look at the carbon. The carbon has access to all of those electrons. Look, there's 8 of them. And the same thing for this oxygen over here, right? It has access to all of those electrons. So by sharing, they're able to fulfill the octet rule. Okay? So what we're going to do here with these drawings is I am going to represent these with lines. When I have a pair of electrons, I'm going to represent it with a solid line. And with that solid line, I can still imagine that there's an electron on the ends of each of those lines. So each line represents 2 electrons. That's important. All right, so each line is what we refer to as a bonding pair. Okay? These electrons that are out here on the periphery, we refer to those as lone pairs. Okay? So there are, so this is what we, prior to this, we've been drawing Lewis dot structures. So this representation is simply called a Lewis structure. As opposed to a Lewis dot structure, this is just a Lewis structure. And there are rules for drawing Lewis structures. And I urge you, if you're listening carefully, and I'm sure you are, and you're taking wonderful notes, I urge you, if you follow these rules step by step to the letter, you will almost always achieve the correct answer. I caution you against doing things that feel right. Don't do this intuitively. Don't do with what looks right. Follow the rules. Okay? So, step one, and this is always step one with drawing Lewis structures. Count up the valence electrons. Total the valence electrons for all of the atoms in your molecule. Okay? And make a total. All right. Step two, draw a skeletal structure. Okay? And you're going to put the least electronegative atom in the middle. In the center. Okay? Now, err on the side of symmetry. Err on the side of... Draw something symmetrical if you can. Okay? That's usually going to get you to the right place. It's very, very rare that you'll draw something that's not symmetrical. Step 3. Subtract 2 electrons for each bond drawn. Okay? You just drew a skeletal structure in step 2. So from your total of the valence electrons, subtract 2 electrons for every bond that you just drew. Step 4. Place any remaining electrons on the outside atoms. To fulfill your octets. Okay? Not hydrogen. Right? And that's important because you need to remember that hydrogen only has a 1s orbital, which means that it can only hold 2 electrons. Okay? This is very important. You will never ever see that. That doesn't happen, nor does anything like this. That doesn't happen. Okay? So, hydrogen can never have more than 2 electrons. Period. End of story. Okay? Now then, step 5. And it seems like there's a lot of steps, but there's only a couple more. Step 5. Place any remaining electrons. So if you've filled your octets on the outside atoms and you still have electrons left over, place any remaining electrons on the central atom. Okay. Step 6. Now we're going to check the octets. and we're going to form multiple bonds if necessary. By borrowing from the outside atom. Okay? And our final step is to check formal charges. Okay? Now, that's a lot of steps, but it really, in the process, and with a little bit of practice, is going to be a piece of cake, right? So let's do some practice, right? So hopefully you've written all these down, all these steps, okay? And if you need to, pause the video and come back and write all those down, because we're going to use those right now, so you're going to want them handy right next to you while we go through this process, okay? Because I'm going to talk through those steps with each one of these molecules, right? So our first molecule we're going to draw is carbon tetrachloride, CCl4, okay? So first, the number of valence electrons, right? Carbon has 4. Chlorine, each of those chlorines has 7. So I have 32 valence total. Okay, so that's step 1. Step 2 says to draw a skeletal structure with the least electronegative atom in the center, right? And between chlorine or carbon, chlorine is farther away from fluorine, so carbon is farther away from chlorine, so carbon is going to go in the middle. And I'm going to draw a symmetrical structure. Okay? So now, the next step says to subtract 2 electrons for every bond that I have drawn. I have drawn 4 bonds. 4 times 2 is 8. I'm going to subtract 8 electrons from my valence, which leaves me with 24 electrons left to put in my drawing. Okay? So now the next step says to place the remaining electrons on my outside atoms to fill my octets. So let's go ahead and do that. So right now, let's zoom in a little bit and sort of evaluate before we move further. Right now, each one of these chlorines has access to 2 electrons, right? So in order to give that chlorine 8 electrons, I'm going to put 6 more around it. Okay? So I'm going to say 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay? So 6 times 4, that takes care of 24, so I have no more electrons to play with, right? So my next step would have been, if I had anything left over at this stage, would be to put more electrons on my central atom. But I've used all my electrons up, so I'm all done, right? So now I want to check my octets, okay? So let's zoom back in here. Take a look. So imagine that each line has an electron at the end of it. That chlorine has access to all of those electrons. And right now, that chlorine has 8 electrons around it, right? So that octet is full, and all of the chlorines are the same. Okay? Now, let's look at the carbon. Oh, stop. Stop. Ah. Sorry, guys. So let's come back to the carbon and imagine that we have a dot at the end of each of these lines, right? And that carbon has access to all of these electrons, right? And if you count, there are 8 electrons there. So all of my chlorines have 8, and my carbon has 8. Okay? So now, the final step, it says to check formal charges. Okay? So there's a method in the book that talks about doing like 1/2 the bonding minus the antibonding, or the lone pairs and whatnot. There's a simpler way to do formal charge. Okay? So formal charge is basically electron bookkeeping. Okay? So we're just going to count electrons. And the easiest way to do it is, I'm going to write this, and it'll make sense after I explain it. Valence minus box. Okay? So the way I have this molecule drawn right now, if I draw a box around one of my atoms and I cut the bond in half, that's what I'm talking about. Okay? So right now that chlorine, what's inside the box is what I'm talking about box. Okay? So chlorine has 7 valence electrons. Right? Just taken right off the periodic table. 7 valence electrons. Now, how many electrons are currently in the box? There are 7. Which means that chlorine has, and all the chlorines have a formal charge of 0. And that's good. Formal charge of 0 is best. Okay? So I'm going to change colors one more time. Let's go to a light green. So now I'm going to do the same thing for the carbon. I'm going to draw a box bisecting the bonds. And I'm going to determine the formal charge on the carbon. So the carbon has 4 valence electrons from the periodic table. There are 4 electrons in the box, which makes a formal charge of 0. Okay? So the lowest set of formal charges, that should be nice, is the goal. Okay? So we won't always have all 0 formal charges, right? But if we can, that is where we want to get to. Okay? So my Lewis structure, however, my correct Lewis structure will not have these boxes, and it may not even have the formal charges. Okay? But what we have drawn here is a correct Lewis structure for carbon tetrachloride. Okay? So let's do a couple more examples. Let's do Dr. Lyon's favorite molecule. How many of you remember? Hopefully it hasn't been too long. H2O. Right? So first step is to total the valence electrons. Each hydrogen has 1, and each oxygen has 6. So I have 8 valence electrons. Right, my next step is to draw a skeletal structure with the least electronegative atom in the middle. Well, since hydrogen's kind of special, I can't do extra bonds with hydrogen. I'm just going to draw something that's symmetrical. Okay? And I'm going to subtract 2 electrons for what I have in the bonds, which means that I have 4 left over. Now I cannot put anything else on those hydrogens, because right now those hydrogens feel like they have access to 2 electrons already, and they're full up. Okay? So I'm going to skip to the next step, which says that I put any remaining atoms on my central atom. Okay? So now I'm going to check my octets, and right now my oxygen feels like it has access to all of these electrons. My oxygen has access to all of that, which means that it has access to 8 valence electrons. Great. It has bonding pairs, and it has lone pairs. Okay, so oxygen has 8. The hydrogens have as many as they can have. They can only have 2 each. So I'm all done. So let's double check with my formal charges. Okay, so let's draw a box. And oxygen has 6 valence electrons from the periodic table. And right now there are 1, 2, 3, 4, 5, 6, which means a 0. Hydrogens, they have 1 valence electron, minus 1 that's in the box, zeros. Everybody's happy. Okay? Let's do another example. This stuff takes a lot of practice. I want to make that very, very clear. Practice with the steps is essential. Okay, CO2. Right, we have 2 times 6 plus 4 gives us 16 valence. Right? I'm going to draw a skeletal structure with my least electronegative atom in the middle and make it symmetrical. Right? So I've drawn a structure with 4 electrons in the bonds, which means that there's 12 left to put on my molecule. I'm going to start with my outside atoms first, and I'm going to fill the octets. Okay, which takes care of all of the electrons. So nothing left to put on my central atom. Now I want to check my octets. So right now, my oxygens have access to all of those electrons. So my oxygens have 8 valence, or 8 electrons around them, right? So the octets on the oxygens are fine. My carbon, on the other hand, only has access to 4. So what I need to do is I need to borrow from my outside atoms and make extra bonds. So what I'm going to do is I'm going to borrow these electrons and I'm going to put them right there in a bond. Okay? Right? So now let's check the octets. Right now that oxygen still has access to 8 electrons, 2 lone pairs and 2 bonding pairs. Right? This oxygen still has access to 8, and carbon has access to 6. Right? So what I'm going to do is I'm going to borrow another set. I'm going to borrow those and put them right there. Now, at this stage, all the species have 8 valence or 8 electrons around them. All their octets are satisfied. Okay, so let's speculate a little bit. Okay, right now, so my last step is to check formal charges. So let's go ahead and do that. If I draw my box, my carbon has 0. My oxygens, my oxygens are also at 0. Now, what if I did what if I did things differently before? And let's say I left this the way it was, and I borrowed an extra set of electrons. Let's make these red. And we did this. Okay? So the way I had it before had formal charges of all zeros. But let's speculate. Let's see what the formal charges look like now. Right? So right now, this oxygen has 6 minus 1, 2, 3, 4, 5. And this oxygen has 6 minus 7. And my carbon has 0. Okay? So my goal is to get the lowest set of formal charges possible. So before, I had 0, 0, and 0. Now, I have plus 1, 0, and minus 1. Not as good. Okay? So the way I had it drawn before was better because it had a lower formal charge. That is how you know that you have the correct Lewis structure. All right, so let's do another example. And let's talk about Lewis structures for ions, okay? So for our chlorate ion. Now when you see that negative charge, that means one more electron, right? So when I total up the valence for this, I'm going to say that chlorine has 7, my oxygens have 6, and there's another one for the negative charge. So we're going to end up with 26 valence electrons. Okay? Now, if you have a positive ion, let's look at an example for that. Ammonium. So I'll have, if I'm positive, I'm going to subtract an electron. So I'll have 5 for the nitrogen, 4 times 1 for the hydrogens, and subtract 1 for the positive charge. Okay? So, little tricky thing, but you need to pay attention to that. If you have an ion, this is important. All right? So let's continue with our chlorate example here. All right, so I have 26 valence. I'm going to draw a symmetrical thing, and chlorine happens to be least electronegative. I'm going to draw something that's vaguely symmetrical. Okay, and I'm going to subtract 2 for each bond that I've drawn. So that's minus 6, which means that there's 20 left over to put on my molecule. So I'm going to fill my outside octets. And I'm going to talk through these steps. I'm talking through the steps every single time that I do this. Filling my outside octets, that takes care of 18. So I've got 2 left to put in my drawing, and those go on the central atom. Okay? So now, let's check the octets. So right now, each of my oxygens have 8, and my chlorine has 2, 4, 6, 8. Everybody's happy, right? But my final step says to check the formal charges. Okay? So right now, my formal charge on my oxygens are all minus 1s. Okay, so minus 1 on that oxygen, minus 1 here, and minus 1 because they're all the same, right? So let's label that this way. Let's look at the chlorine on the other hand. 1, 2, So right now the chlorine has 7 minus 5, which makes it a plus 2. Okay? So can I get that lower? And the whole point is that my formal charges should add up to my ion charge, right? So I've got +2 -3 should give me a -1. Great, cool. But can I get those formal charges lower by changing my bonds? Let's see. All right, so if I borrow from some outside atoms and make extra bonds, now let's check the formal charges. This one, 6 - 6, these are still -1s. And if I look at the formal charge on my chlorine, now it's a 7 - 6, so it's only a +1. Right? So I'm getting closer. Now, what happens if I do another double bond? Let's see that. All right? So if I borrow from my left-hand oxygen and make another double bond, now I'm going to have formal charges of zeros, a -1 here, and I've got 1, 2, 3, 4, 5, 6, 7. Now my chlorine also has a 0. All right? So my goal is to get the lowest set of formal charges. Great. So now I've got all zeros and a single -1. Everything's happy. So here is my final drawing, and I need to encase it because it's a negatively charged ion in brackets. All right? Now, what I've done here is right now my chlorine has 2, 4, 6, 8, 10, 12 electrons around it. That's a lot, okay? Here's the deal with the octet rule. Everyone except hydrogen must, that's a big must, have at least an octet. Okay? Must have at least an octet. But elements in the third row and lower can exceed that. Okay? Must be third row. Boron, carbon, oxygen, nitrogen, and fluorine cannot exceed the octet rule. Okay, so second row elements must obey the octet rule. Anything third row and lower is allowed to violate the octet rule. We can say this violate. Okay. Now, other exceptions, and there are a couple of them. One of which, boron. Boron only needs 3 bonds. Okay? It's perfectly happy doing 3 bonds. So in other words, a 6 instead of an 8, right? So example, boron trichloride is a very normal compound. It has 24 valence. If I draw a structure, -6 in the bonds, means there's 18. I fill my outside octets. That takes care of all my electrons. There's nothing left to put on the central atom. Now, normally my next step would be to make sure that everything has at least an octet. But boron is an exception. And it's just one that you have to know. Okay? That's one that you just need to have memorized, is that boron is perfectly happy having less than an octet. Right? Our next exception are odd numbers of electrons. All right? And what we have when in the situation of odd numbers of electrons, you have what are referred to as radicals. Okay? And if you've watched TV really at all in the modern age, you've probably seen some kind of cosmetic commercial that talks about free radicals. And this is exactly what they're talking about. All right, so let's look at an example of nitrogen monoxide. Okay? It has 11 valence electrons. All right? So if I want to illustrate the point here, follow the rules. This is totally normal. Just follow the rules. So my step 1 is to total the valence electrons. Step 2 is to draw a chemical or a skeletal structure. Subtract 2 electrons in the bonds, which means that I have 9 electrons left to put on my atom or my molecule. I'm going to fill my outside atoms first. My nitrogen is least electronegative, so it is a quote-unquote central atom. So I'm going to put electrons on my oxygen first, which means that I have 1 electron to place on my drawing. Or excuse me, I've done that wrong. 6. Which means that I have 3 left to put on my drawing. Those go on the central atom, in this case, the nitrogen. Okay? So, nothing special. I'm not doing anything weird yet. Right? So now I need to try and fulfill my octets. So right now my nitrogen has 2, 4, 5 electrons around it. So I'm going to borrow from my oxygen and make another bond. Okay? Now, if I borrow again, because right now my nitrogen has 7, but if I borrow again, let's see what happens. If I borrow again, now what have I done? Now I've got 2, 4, 6, 8, 9. I have violated the octet rule. And I cannot do that with nitrogen. Okay? Nitrogen must follow the octet rule, even if it means that it comes out having less than an octet. That's what you got to do. You cannot exceed the octet rule with anything in the second row. Right? So we're going to get rid of that bond. We're going to put the electrons back on the oxygen. And we have nitrogen monoxide. Okay? So because of this, that makes this very reactive. Right? That single electron does not like being by itself. All right? It's going to try and jump off and react with something else as soon as it possibly can, which is why radicals are so reactive, because they have single electrons and they don't stay radicals for very long. So that's why we talk about them in cosmetics ads, because they're very reactive. Okay? So now, let's talk about a thing called resonance. All right? Resonance is sometimes a rather confusing topic for students. Fair warning. Right? So let's look at an example of a thing called an allotrope of oxygen and that is ozone. Okay, and what an allotrope is when you have, let me pull up my definition real quick. Well, I guess I don't have a definition with me. Thought I did. But anyway, allotropes are when you have multiple versions of naturally occurring elements. Okay. Normally, oxygen is O2, right? That's the naturally occurring version of oxygen. But you can also find oxygen in nature as O3. You can also have allotropes of sulfur. Sulfur has lots of them, 6. All the way up to like S10, okay, which was my first truck in a Chevy S10. But an allotrope of oxygen is that we're going to work with in this example is O3. So let's come back to that situation, right? So if I were to draw a Lewis structure for ozone, I am going to draw, if I were to go through the process, I could draw one that looks like this. Okay, but I could just as easily draw one that looks like this. And I would not be incorrect for doing so. Okay, these are equal. Both of these are correct Lewis structures. Okay, and what that means is that they are resonance structures. Okay, anytime you have multiple correct Lewis structures for a single molecule, that is resonance. Okay, so a thing that is important about resonance is that these exist simultaneously. Okay, this isn't like a light switch where it goes on and off. That bond is not flipping back and forth. The reality is that this Lewis structure looks something more like this, where you have partial bonds, right? 1.5 partial bonds. Instead of a single bond and a double bond, you have 2 1.5 bonds. Okay? But, and this is important, is that we never draw these. Okay? So, if you're listening carefully, I hope you are, is that we never draw this. Okay? Understand that this exists, but never draw it when you're trying to draw Lewis structures. Okay? So, this sort of leads us into the next topic, which is bond lengths and bond strengths. Okay, so bond lengths and bond strengths. So imagine, if you will, your bond is like bungee cords, right? And if you have a single bungee cord, you can pull it and stretch it, as far as the bungee cord will let you. But if you have 2 bungee cords, it's gonna be a little bit harder to stretch quite as far. And if you have 3 or more bungee cords, it's going to be even more difficult to stretch. So you can think about your chemical bonds your covalent bonds in much the same way. So with bond lengths and bond strengths, a single bond, I don't know why I put a 1 there, let's take that away. A single bond is the longest and weakest. Okay, that's the analogous to the single bungee cord. Okay, a double bond is shorter and stronger. A triple bond is the shortest and strongest. Okay, and there's a thing called bond order. Okay, and you're not required to calculate bond order, but I just want to touch on it really quickly because it's kind of a cool thing. So bond order of 1 is a single bond. Of 2 is a double. And 3 is a triple. Okay? And the way bond order works is you can actually calculate bond order from the from your drawing. So bond order is the total number of bonds divided by the number of bond areas. Okay, so let's come back and look at our ozone molecule again. Okay, so if I want to know the total number of bonds, I have 1, 2, 3 bonds. Okay, 3 bonds. And the number of bond areas, whoops, the number of bond areas, those are the regions of the bonds, right? So there's 2 bond areas. That gives me a bond order of 1.5. Okay, so let's come back to our sort of definition of bond order. So if I've got bond order of 1 as a single and bond order of 2 as a double, then somewhere in between is a bond order of 1.5, right? So thinking about resonance, right? And I told you never to draw this version, but each of these is 1.5 bonds. Comes from the bond order. Okay? So like I said, you do not have to, I think anywhere in the mastering, deal with bond order, but you could if you wanted to. Okay. Now, that pretty much does it for us with this lecture. There's one more topic in this chapter, but we actually inadvertently covered it before we left for break, and that's bond enthalpies. Right? And remember, bond enthalpies follow Hess's law. And the idea is that delta H for the reaction equals bonds broken minus bonds formed. right? And some of you that were in class, if you're watching this, you probably remember this was the day that my supervisor was there and was evaluating me, and you guys were making my life wonderful. Incidentally, that evaluation went quite well. But let's take a look at an example here before I finish this video. So looking at a reaction of this molecule with water, making this molecule. Okay, so let's think about what bonds are being broken here and what bonds are being formed. So bonds broken, we've got this one, and we've got this one. Okay, and then formed over here, we've got one of these, and one of these. Right? So looking at the fragments, we want to pay attention to how this thing comes apart and then gets reassembled. Okay? And so we would look at bond energies. And they're always given to break. Okay? So when you look up these tables of values, we get all kinds of numbers, but the tables give us the energies in terms of energy to break bonds. So let's take a look at that business. So breaking, let's come back to the red. We have the energy to break a C double bond C is 611 kilojoules per mole. And to break an HOH, 464 kilojoules per mole. Okay? And then we keep looking on the table and we find the energy to break a CH bond is 414. The energy to break a COH bond is 360. And the energy to break a CC bond is 347. But remember, these are, we want to form these bonds, the CH and the CC and the COH. We want to form those, right? So to form those bonds, I need to make these negative, right? Remember, delta H for the opposite process is the same value but opposite in sign. So when I total these up, I get 1,075 to break. And over here I get negative 1121 to form. So my delta H of reaction, bonds broken, minus bonds formed, equals negative 46 kilojoules per mole. Right? So it's an exothermic process. Okay? So I want you to hopefully remember that process. Maybe it was a little bit strange when we were in class that day, but dealing with the bond enthalpies